speak about lower mean curvature bounds for subsets in RCD spaces.
Yeah, thank you for the introduction, and yeah, thanks for to the organizers to give me the opportunity to speak here. Yeah, I'm sorry that I cannot be in Toronto, so I was there last week, but unfortunately I had to go back. So, but yeah, I still can do the seminar here. So I will speak about lower, as the title says, about lower mean curvature bounds for subsets in RCD spaces. And so the plan of the talk will be roughly like this. So I mean, first I will review some results about Riemannian manifolds with lower Ricci curvature and boundary. Then I will explain how we can define mean curvature bounds for subsets in RCD spaces. And then finally, I will explain about uniform convergence and stability of mean curvature bounds. Okay, so let's start. So I will start with some motivational slides. So we all know, I mean, when you have a Riemannian manifold with empty boundary and a lower Ricci curvature bound, we can prove very nice results, or theorems are proven. So for instance, we have the Bonnet-Myers estimate that tells us that under a positive lower Ricci bound, the diameter is bound from above. And we have equality in this estimate if and only if we have a sphere. Another theorem in this class is the Giga-Cromwell splitting theorem. Okay, so and the question now is, can we generalize, or can we obtain similar theorems in the context of Riemannian manifolds with boundary? And especially we want to consider not just convex boundary, manifolds with convex boundary. So we want to consider Riemannian manifolds with non-empty boundary and some additional curvature assumption on for the boundary that is weaker than convexity. And for that, we will consider the mean curvature of the boundary, and that is just to remind you, this is the trace of the second fundamental form of the boundary. Okay, and then if we now assume in addition to lower Ricci bounds, a lower bound for the mean curvature, indeed there are also similar, one can obtain similar results, like in the case of like in the non-boundary case, and yeah, results in this context, results in this context were proven by Casue I think that was in 1984. And he proved, for instance, this theorem. So if you have non-negative, so imagine you have a Riemannian manifold with boundary, a smooth boundary. And now assume you also have non-negative Ricci curvature. And the mean curvature is bounded from below by a positive constant h. Then what Casue proved is that you get an upper bound for this expression that you can see here. That is better understood in the following way. So the infimum here, this is nothing else than the distance to the complement, or the distance to the boundary. So the minimal distance of each point to the boundary. And then the estimate says that this function has a uniform upper bound that only depends on the dimension and the mean curvature. And here in this estimate, one also has a rigidity statement. So we have equality if and only if the manifold with boundary is isometric to a closed ball in Euclidean space. And this estimate geometrically can be understood as a bound for the radius of balls that you can pack into your manifold with boundary. So so we also speak about inscribed radius bounds. Okay. Other results in this direction that were also proven by Kazue that generalize the splitting results are the following. So if we have non-negative Ricci curvature and non-negative mean curvature, and we know the boundary is disconnected and also compact, then Kazue proved that the space splits, and more precisely, there's another Riemannian manifold with non-negative Ricci curvature such that M is isometric to the interval times n. So this is in the compact situation, and what you can see is that, I mean, there's no a priori number on the number of boundary components is a priori not fixed. But the result tells you that, I mean, there can be only two.
Hi, Christian, sorry. Christian.
Yeah.
Okay. So I'm confused about this statement on the splitting. Don't you need some sort of line or long geodesic or anything like that?
No. No, this works without any assumption. Yeah, let me say one more comment. So this is this theorem is in the, but thanks for the question. Yeah, this theorem is in the spirit of similar results for, or not similar results, but related results for the scalar curvature. So there's this famous result by Schoen, Yao, Gromov, Lawson that you cannot that any non-positive, how is it called? Any non-negative, any Riemannian metric of non-negative scalar curvature of the torus.
Yeah. Okay. The one on the torus, you mean? The scalar curvature is negative on the torus, then it's flat.
Yeah, yeah, and this is somehow the mean curvature analog of this theorem.
Okay, thanks for this comment. Thanks.
Yeah, you're welcome. Yeah, and so this is the compact situation, and the non-compact theorem is the following, where you now in fact need a line, or more precisely a ray. So you have a Riemannian manifold with non-negative Ricci curvature and non-negative mean curvature, and if you know there exists a geodesic ray with initial point in the boundary, then you split. You also split, and you split off a half line. And here the interesting thing is that you do not need to assume compactness. So this works without that the boundary is compact. Okay. So this is for motivational purposes, and now. Yeah, the goal in my talk is, so we want to generalize these results to the non-smooth setting of RCD spaces, RCD metric measure spaces, and here I have to say, so these theorems were already generalized, let's say, to the setting of Bakri-Emry weighted Riemannian manifolds. This was done by Sakurai, for instance.
So sorry. Can you go back to the previous theorem with array? What is it?
Yeah. What is the question? So
this seems wrong to me. Wait a minute.
Okay.
I mean, even if you have even if you have non-negative sectional curvature and convex, not just mean convex boundary, then just existence of array doesn't imply any splitting. You can have, I don't know, like, take y equal to x squared and something in R2 and above the parabola, like,
Yeah.
That has Ricci curvature 0, convex boundary. There is a ray, it doesn't split. Well,
Yeah, you're right.
something is wrong. There should be some more assumptions here. It cannot be just like this.
Yeah,
I'm not
maybe
sure what they
you're
should be, but
Is the mean curvature reversed though?
no, I'm pretty
no.
sure it just mean convex. And what I was suggesting is just to take a convex boundary, right? So that should be special case.
Yeah, okay, you're right.
I feel
okay,
like there
maybe-
is some assumption missing, but I don't know what it is.
I feel like the mean
May-
curvature is just in the other direction than what.
No,
Well, maybe it's compactness, like in the statement above, right? You cannot make with a compact, you know, I think in your example, Vitaly, it's really important that you have the graph, you know, of a full function. Otherwise, if you insist maybe on a compact boundary.
well, but no, this thing is not compact, right? I mean,
Exactly, that's what I'm saying. That's what I'm saying. The boundary. The boundary.
I'm not sure what one needs to assume in addition here. Something is missing in this assumption. That's all.
Yeah, you're right.
I don't know what.
I mean, maybe
Anyway.
yeah, thanks. So probably it's compactness of the boundary. Yeah, I didn't think about
of the boundary. Oh, compactness of the boundary.
Yeah. Yeah, I think I
Correct.
would need I need to check how the proof works again. So one needs to use the maximum principle at one point, and
yeah, okay. If there is a compactness of the boundary, then yes, yeah, that should be true. Okay.
Yeah, so I mean, it's definitely true if the boundary is compact. If the boundary is not compact, you're right, one needs one more assumption. Yeah,
okay.
Thanks. Thank you. Okay, so let's continue. So I mean, my main motivation here is I want to prove almost rigidity statements in the spirit as we have for, let's say, as we like we can prove for Riemannian manifolds by contradiction arguments. And so for that, it's, yeah, so this is the motivation why we would like to generalize these theorems to a non-smooth setting. So this, of course, raises a lot of questions that I will try to address later in the talk. But let's first think what would be the right setup here. So let me briefly recall again synthetic Ricci curvature bounds, or let me just jump that slide, because I guess since last week, I mean, we all know now synthetic, we know the curvature dimension condition and the Riemannian curvature dimension condition. So I skipped that, but let me recall two things from the calculus of RCD spaces. So first thing is, so we have an inner product. So we can pair two Sobolev functions such that we can make sense of an inner product between their gradients. And the second thing is, with this inner product, we can also make sense of the distributional Laplace operator. And more precisely, we say that, so given an open subset in X, we say that F is in the domain of the distributional Laplace operator if there exists a Radon functional such that we have this identity here for all Lipschitz functions with compact support in omega. And I apologize here, this is very, I mean, this is, so I don't explain anything here, so I will not explain what's a Radon function, and I also will not say how one should understand, how this is understood. So especially, I think when we are in the n equal infinity case, one needs to assume something better here for the test functions, but I hope this is sufficient as an explanation. And let me also say the first time when this was used in the RCD context, I guess, was in a paper by Nicola. Okay, so then let me go to the next slide. So, yeah, okay, and I also apologize for the crappy pictures. So first, unfortunately, the RCD spaces is not quite the right setup because, I mean, in general, if we have a Riemannian manifold with boundary that just has a lower bound on the mean curvature, this will not be an RCD Kn space in general, or even an RCD K infinity space, because in general, then I mean, this is not so hard to see, but one reason why this is the case is that the relative entropy is not semi-convex. And this is illustrated by this picture that you can see here. So if you have, so the picture is not quite what we want to look at, because here the boundary is even non-convex. And so here the boundary is not real, or let's say it's not really mean convex also. Or I mean, okay, it has a lower mean curvature bound, but it's in the plane, so it's not quite what we should imagine. But you can see that the non-convexity of the boundary forces geodesics to touch the boundary and in a very bad way, or in a bad way for the entropy. So if you want to transport these two measures that you can see here onto each other, then the T midpoints in the Wasserstein space will be very concentrated and in the region where the geodesics touch the boundary, and in this region the entropy will explode. So therefore you cannot expect entropy convexity. So therefore, what I suggest to consider is we look at pairs. So the pair is first an RCD space X together with an open subset in our space. And for this open subset, we want to define what it means to have synthetic lower mean curvature. What it means to have mean curvature bounded from below, or more precisely for the boundary, but I will not distinguish, so I will say that for omega or also for the boundary of omega. Okay, so this is what we want to do in the following. So how can we define a lower mean curvature bound for such subsets? So therefore, let's consider such omega inside an RCD space, and we assume that the complement of this omega is non-empty. And if this is true, then we can define the distance function to the complement of omega. So this is given by this definition that you see here. And this distance function is always 1 Lipschitz. So this is clear, and it's also, because of that, it's also a Sobolev function. And what we also know, and in RCD setting, this, I guess, was first proved or used by Cavaletti and Mondino, is that this distance function to the boundary, if we restrict it to omega, is in the domain of the distributional Laplace operator. And in fact, the distributional Laplacian of this function is a signed Euler measure. Okay, so let's keep this in mind, and let's go back to the smooth setting for a moment. So we have the following lemma. So let's consider a Riemannian manifold with non-negative Ricci curvature and some omega that has smooth boundary. And then the following is true, that the mean curvature of the boundary of this omega is bounded from below by H if and only if the distributional Laplacian of the distance function to the complement of omega satisfies this estimate here in the sense of measures. And in particular, you can see that if H is 0, then this exactly means that the distance function to the boundary is subharmonic. So this is this can be further generalized. So I mean, non-negativity of the Ricci curvature doesn't really play a role. So more generally, if the Ricci curvature is bounded from below by k, a similar statement is true with a more complicated formula here. So where you can see we use this functions S that depend on two parameters, kappa and chi, and it's defined here with this generalized sign function that is a solution of this ODE that you see in the last line. Okay, but most of the time it will be sufficient for us to consider non-negative Ricci curvature. So so you don't need to memorize this formula now, or I mean it will appear again, but I mean it doesn't matter so much. But this lemma is now very interesting because I mean we start here with a smooth with omega that has a smooth boundary, but this estimate for the distributional Laplacian now makes sense without any smoothness assumption. So and we saw a second before that we can our distance functions for such omegas in fact have a distributional Laplace operator, so it's well defined. So therefore it makes sense to make the following definition, and it's perfectly meaningful in RCD context now. So that that is we say omega has a subset in an RCD Kn space where omega where the complement is non-empty, has mean curvature bounded from below by h if and only if this estimate for the distributional Laplacian holds in the sense of measures. So this is our definition for mean curvature that we want to use in the following. And so let me make a few comments. So first comment is there's a different notion of mean curvature that I introduced some time ago using 1D localization, and similarly also Cavaletti-Mondino in the context of Lorentzian length spaces. And independently, also with Annegret Burtscher, Robert McCann, and Eric Wulger, we refined this notion that I gave before, and this uses 1D localization, and it's also very useful, but it requires a little bit of regularity for omega. And under this regularity, one can prove that this notion of mean curvature via 1D localization is in fact equivalent to this Laplace estimate. Okay, second remark is that do we actually have such sets in RCD spaces? And the answer is yes, and there are many examples, but one particular example is given by Mondino Simola, who have the following very nice result. They prove that if we have a subset omega that has a locally minimizing parameter, so the parameter here is kind of the functional analytic notion of boundary, then this omega has non-negative mean curvature in the sense of the definition here. So they in fact exactly prove this estimate here. But let me say this Laplacian estimate, I mean, it already appears in the paper that I wrote together with Burtscher, McCann, and Wulger. So I mean that this is related to mean curvature was already known to us, and then the final remark here is so the relation to the intrinsic boundary of this notion is an open question, or more precisely a conjecture I think the first time appears in the paper by Brouet, Neighbor, and Simola is that the intrinsic boundary, let's say in the sense of Gili and De Philippis, or is mean convex, or sorry, the intrinsic boundary in RCD KN space in the sense of Gili and De Philippis is then the intrinsic boundary is mean convex. Okay, so these are the definition and remarks about it, and with this definition, I'm now I was able, or I could prove this generalizations of these results that you saw before, where okay here still we have this this statement where I just assume we have array.
So question.
Yeah.
So maybe I missed it. You said something. Let's say you are in a smooth manifold, and then you have some domain such that the distance but without say smoothness assumptions on this domain, such that the distance to the complement is well, has this Laplacian bound. Can you then say that it's in some sense I mean it doesn't have to be even smooth, right?
Yeah, so I mean, so first of all, this is a condition I just assume now for sets, of course. I mean, but the result of Mondino and Simola before, I mean, tells you that if you have a set that is locally parameter minimizing, that even in a Riemannian manifold, then it will be okay in a Riemannian manifold. Okay, you're smooth automatically. Yeah.
I'm sort of asking about the converse. Well, maybe it's not known. It should be true. Yeah, I was just wondering that if you can go the other way, that if you have this condition, then your this in some sense should be sort of mean convex in reasonable sense, right? Maybe by smooth approximation.
Yeah, okay. I mean, I'm not quite sure.
I'm not sure how to say it, yes.
Yeah, what you mean then with mean convex, because I mean, I make this definition because if the omega is not smooth, then I cannot, so what is a priori mean convexity for non-smooth sets?
Right, that's not completely clear, but it should be maybe approximatable by if you step inside, then it should become smooth and have actual mean convexity. But
yeah,
almost. Anyway.
Okay. Yeah. Yes. Sorry. Thanks. I understand your question also. Yeah, you're right. There is this notion of let's say mean convexity for varifolds, I guess. I mean,
right.
So
it should be
think,
something.
Yeah.
Should be relatable to all those notions.
Yeah, it's a good question. So I mean, maybe yeah, I didn't think about it, but it's a good point. Thanks. Okay. Yeah. So this is the theorem I could prove. So I mean, in the second case, in the non-compact case, as Vitali mentioned, one should probably or one should add another assumption, otherwise it's wrong. So probably compactness of the boundary sounds reasonable.
Well, compactness will certainly be enough, right? I mean, if it's because if you double it, then you'll have a line, and then it will split.
No, but I mean, you cannot double it. I mean, it's when you double it, mean convexity doesn't give you a space with non.
Oh, sorry, this is
negative.
in RCD. I was thinking about the smooth case, right? In smooth case, you can double, right? I was talking about consortium or whatever you were mentioning.
No, but even in the smooth case, if you double it, I mean the double of a thing with just mean convex boundary is not it's not a generalized. It's not a space.
Oh, right. Yeah, you need actual convexity, right? Okay.
Yeah. Yeah. Okay. Okay, but you can forget about the non-compact case because from now on we only will consider compact spaces. So so only the first statement will be actually the one we keep in mind now. So that means if we have mean convex boundary, omega is connected, the boundary is disconnected, then it splits off. Then omega splits with such an interval. Okay, so so then then we come to the second part of the talk that is about stability. And so this is kind of, yeah, so this was something I was trying to understand. So, and what I present here is one way you can think about it. So, I mean, but maybe there are other ways you can do it. But let me try to convince you why the way I think about this might be the reasonable or the best way to think about it. So let's look at constants here, k, h, d, and n, and we define the space of all, and we define here x, k, and d is the space of all RCD spaces, RCD Kn spaces with diameter bound from above by d, and we assume these spaces are normalized. So they are always compact and have finite measures, so we can do this normalization. Then also we define the space y, k, and dh. And this is now what I said before, the space of pairs, where we have an RCD space and a subset omega inside of the RCD space that has mean curvature bounded from below by h. Okay, and now we want to define a topology on this second family Y, and this is and the way how we do it is as follows. So we pick two RCD spaces x0 and x1, since they are compact, they are always have finite Gromov-Hausdorff distance to each other. So we fix this distance that we call it small d here, and then we can find 2R Gromov-Hausdorff epsilon isometries that allow us to estimate the Gromov-Hausdorff distance, where R here is bigger than d. So this we can always do. And then in the second step, we look at two functions, continuous functions, and for simplicity non-negative on x0 and x1. And what we define now is this quantity as psi here. So this is supposed to generalize kind of the uniform distance between two functions that live on the same space. And to do that, we look at this modulus of the difference between fx and gy, where x is in x0 and y is in x1, such that x mapped with the Gromov-Hausdorff isometry psi is at most 2r, has at most distance 2r from y. And we can do the same thing for phi in the other direction. Okay, and now we define the uniform distance between f and g in the following. We take the maximum between these two quantities, s psi and s phi, and then we take the infimum with respect to all pairs, psi and phi, that are 2R Gromov-Hausdorff isometries between our spaces, where R here is bigger than the Gromov-Hausdorff distance between x0 and x1. So I hope this makes sense. And so this is just the distance that metrizes, that is a distance for uniform convergence. And so let me list some properties. So first, it's symmetric. Then, I mean, the sum of this uniform or this d infinity distance with the Gromov-Hausdorff distance is 0 if and only if x0 and x1 are isometric and f equals g. And we also have a triangle inequality. So this is not so difficult to prove.
So on the previous slide, if in this last definition, I mean, so the f and the g have to be reversed in one of these things under the max, don't they? Or maybe I don't understand.
Yeah.
Yeah, the phi and the psi are going in opposite directions, right?
Yeah.
Okay.
Exactly.
And what it means to be a 2R Gromov, or rather an R Gromov-Hausdorff isometry, is that you're an isometry up to an error R, and you cover the target up to an error R, right? So,
yeah,
so the
exactly.
constraint on the S psi is somehow has to do with the sets points that you miss or something. I'm not sure. I mean, what is the restriction? The dx1 of psi of xy is less than 2R. Is that a restriction if psi is an R Gromov-Hausdorff isometry?
Yeah, thanks for the question.
Restriction. It's a restriction on the pairs of points that you look at. Okay, I see.
Mm-hmm.
All right, thanks.
Yeah, you already said it. So I mean the 2R Gromov-Hausdorff isometries, or also called epsilon Gromov-Hausdorff isometries. I mean the images are epsilon nets in your target, and so this constraint here on the points x and y is actually not empty. So I mean we find these points, and so we can make sense of this supremum. Okay. More questions? Okay. So we have these properties, and now assume we have a sequence of Gromov-Hausdorff space, of RCD spaces xi that converge to in measured Gromov-Hausdorff sense to an RCD Kn space x, and so this distance is now defined exactly in a way such that it somehow, so we can formulate, how do I say, we can give a version, or not a version, but it's exactly the Gromov-Hausdorff, the Gromov-Asela-Ascoli theorem that I guess many are familiar with. So that is, so if, for instance, if we have a sequence of one Lipschitz functions on our space xi, then this sequence of functions fi subconverge with respect to this d infinities distance to a one Lipschitz function f on the limit space. So it's a reformulation of the Gromov-Asela-Ascoli theorem.
I guess the sequence better be bounded.
Yes, true. Yeah. I mean that the spaces are bounded, and so the sequence is already bounded.
But you don't want a sequence of constants that goes to infinity. I mean.
Yes. Yeah. True.
I mean, it's usually stated as xi to a constant, to a compact metric space.
Sorry, can you say that again?
It's usually stated as xi mapped to a compact metric space.
Ah, yeah. I see. Yeah.
So whatever, compact set in R.
Yeah, thanks. Yeah, so yeah, that is true, but it will not play a role for what comes next. So so therefore I didn't think about it, sorry. So what we so because of this theorem, we call this now uniform convergence in the Asela-Ascoli sense. So this is at least how I call it in my paper. Maybe this is also like it was named before. And so the relation to this omegas that I showed you before is now the following. So if we have such omega i's as subsets in our spaces xi, such that the complements are non-empty, then we find in the limit space X an open subset omega that has non-empty complements, such that the distance function to the complement of omega I converge to the distance function to the complement of omega with respect to this d infinity distance, or with respect to uniform convergence in the Arceli sense. Okay, so this is good because it preserves this structure of pairs that we saw before, next thing is also what is the relation to mean curvature. So let me give you, before that, let me introduce this new distance script d here. So here you see this should be actually the uniform distance between the distance functions, sorry. So the script d is simply the sum of the measured Gromov-Hausdorff distance between x0 and x1, and the uniform distance between the distance function to the complements of omega 0 and omega 1. I hope that is clear. And then let's continue. So then we have the following theorem. So if we have such a sequence of pairs xi omega I that converges to x comma omega with respect to this d distance, then the following is true. If we know that this pair xi omega I was in this class of pairs where the omegas have a lower mean curvature bound, that is h, then also the limit satisfies this. So this is the important theorem here, so that mean curvature bounds are preserved under this convergence that I just defined. And the sketch of the proof the proof is actually fairly simple. So this uniform convergence of the distance functions implies W12 strong convergence of the distance functions. So I will not explain what it is, but it's kind of, so we'll have convergence along the sequence. And this, and the second point is that under this convergence, the inequality that we have for the Laplace operator is preserved. And also let me say, this is not something that, or let's say this is something that was observed before in other papers. I proved it independently from these other papers, but I think it appears in some form already in a paper by Ambrosio and Honda, and also in the paper by Poe, Neighbor, and Simola. So they also use this stability of the Laplacian. Okay. But together with the stability and Gromov-Arceli theorem, we have the following nice compactness theorem. So that is this space of pairs of RCD spaces together with subsets that have mean curvature bounds. This is compact with respect to this distance d. And again, here, let me maybe write it again. So this here is not, this here should be the uniform distance between the distance functions. Oh, no. Yeah. Okay. Please interrupt me if I'm over time. So this is now nice because we have a compactness result, which brings us pretty close to what we are actually looking for. That is an almost rigidity statement. So so the problem now is the following. So I mean this notions of convergence is very nice. It preserves the mean curvature and everything, and it has a compactness statement. But what happens is the following. Maybe I didn't have the right picture. Do I have the right picture? No. Yeah, so what happens is, so before I come to the next definition, is that this in the limit, even if you start with omega i's that are connected, in the limit, it might happen that the omega is not connected anymore. And if you go back to the theorems that I showed you, the rigidity theorems, connectedness of omega was crucial because we want to apply a maximum principle, and without connectedness, the theorems are simply false. So therefore, to have an almost rigidity statement, and using the rigidity statements you saw before, we need to add in a condition that guarantees that we do not lose connectedness in the limit. And the definition I propose is the following. So this is what is already appears in the literature, and it's called C uniformity. So if we have a geodesic metric space X and an omega that is a subset, we call it C uniform. If the following is true, and just let me explain it. So it means that between any 2 points in our set omega, so x and y, we find a rectifiable curve that connects these 2 points, but also this curve satisfies this estimates here, which essentially means that not just the curve is in omega, but this blue banana that you see here is in omega. And then this is in a quantitative way. I mean, this is given in a quantitative way because we have this constant C here. So this is a nice condition because first, I mean, it's easy to check. I mean, we can see with our eyes if something is C uniform. And the second thing is also that it's preserved under this convergence that I defined. So that is, if we have a sequence xi omega I that converges to x omega, then the limit and the omega i's are C uniform, then also the limit is C uniform. And this is now sufficient to state and to prove a theorem that we are looking for, that is an almost rigidity theorem under lower mean curvature bounds. And it's in the one such theorem is this here. So we have let's consider or let's have constants d, c, small d, n, and so on. And then for all epsilon, there exists a delta such that the following is true. If we have a pair x omega in this class that almost satisfies in this class y, almost satisfying the curvature bounds in the rigidity case, and such that omega is C uniform, and also omega, the complement of omega is a disjoint union of sets where the number of components is k bigger or equal than 2. And we also assume that they all have a definite distance from each other. Then the following is true, that first of all, the k is actually just 2. And second, we find a space or a pair set omega infinity such that, and another space y, such that the omega infinity here is isometric to this product here, where we here have isometry not with respect to the distance on X, but with respect to the induced intrinsic distance in each of these sets. And X omega is infinite d distance here to the pair Z omega infinity. And that this is true, you can now easily check by a contradiction argument. Because we have all the ingredients that allow us to apply the rigidity theorems that you saw before. Okay, so I'm almost done. Let me give you one more point that I want to mention here. So this is this picture here. We have this notion.
So we're running over time, Christian, and we have to move to the other building for Nicola's colloquium. So can you wrap it up in about a minute or less, do you think?
Okay, then, yeah, in less than a minute, yes. The problem here is this condition C uniformity. If you think about it, I mean, it's actually too strong. I mean, way too strong, because it rules out this example that you see here. This example is perfectly fine with respect to our convergence notion here, but it's not allowed under C uniformity. And something I try to do in the future is to replace the C uniformity by a weaker condition or by a different condition that also would allow examples like this here. Okay, and that's everything what I wanted to say. And thanks, and yeah, thanks for all the questions.